Dear colleagues, I want to present you our paper that called Mathematical Model of Subpopulation Dynamics in Case of Different Niches for Subpopulations. The authors are Alexander Kuzenkov, Mykola Triputin, Vitaly Kuznetsov, Olena Hulesha, and Viktor Artemchuk. The presenter is Vitaly Kuznetsov. The study examines of population divided into interaction subpopulations that differ in lifestyle, habitat, and competition level. Individuals may transition between subpopulations with certain probabilities since a group are not reproductively isolated. The model describes subpopulation dynamics where X is the size of subpopulation, GA is a reproductive coefficient, C characterizes inter-subpopulation competition, and A defines transition probabilities between groups. Subpopulation may differ in reproduction, transient coefficients, and initial size. The system is generalized Lotka Voltaire model, whose main share is unequal competition coefficients for different subpopulation, reflecting differences in perception of external influence. Stability and equilibrium state are analyzed using the Lyapunov approach. The system has n plus 1 isolated equilibrium points, including the origin. For case when n equal to, the dynamic system has the following form that you can see the equation 1. At the origin, the Jacobian matrix of the system 1 will take the form that you can see on the slide, the system 2. At singular points 3 and 4, it will take the following form accordingly. The characteristic equation of system 1 takes the following form 5 that you can see on the slide. The components of the Jacobian matrix of dynamic system are generally as follows. 1, when n equal 2, we have the second equation, the second system. And this table present for us the coefficients of characteristic polynomial of the Jacobian matrix for three equilibrium points of system 1 on slide previous slide number 3. Theorems 1 and 2 provide for n equal to the equilibrium point at the original is null under condition 2 and focus under condition 3. The equilibrium is stable under condition 4 and unstable under condition 5. Bifurcation occurs when at least one variable of the Jacobian matrix becomes zero. A transition from null to focus is also identified. When the reproductive parameter A1 crosses zero, the system undergoes a saddle node bifurcation. The non-zero equilibrium points disappears from the first quadrant, and the free space topology changes. At case the first E equals 0, the non-zero equilibrium migrates with the origin forming a degenerated equilibrium state. In theorem 3 and 4, it is proven that the system of differential equation for n equal to is degenerate in the neighborhood of the singular point under condition 1 is a saddle under condition 2, is a node under condition 3, and is a focus under condition 4 that you can see on the slide. Moreover, the node and the focus of are stable in condition 5. holds and unstable if condition 6 holds. Except the considered cases, another type of bifurcation can occur when you have the case number one. In this case, the critical value of the parameters of determined by phone quantity 2, then you can see on this slide, it is obvious that in the vicinity of the point 2, the discriminator of the characteristic equation is negative. Uh, the singular point is a focus. Bifurcation in this case is change of the stable focus and unstable one of vice versa. Figure that you can see on the slide shows for us the case of such a bifurcation when parameter lambda passes through the critical value 0. Other parameters are selected as false the 3. The bifurcation that was presented above occurs if the size of one of subpopulation decreases and the other states the shortage in the first one. When passing through the bifurcation value, the system changes the growth trend from positive to negative or vice versa. Thus, either the development of subpopulation manages to compensate the losses of declining subpopulations that you can see on this figure, all due the part goes to the dynamic subgroup, the sizes of both subgroups approach 0 over the time that you can see on this picture. It should be noted that the stability of a singular point of origin is sufficiently local. Thus, with a slight deviation from the origin, the topology of this space changes that you can see on this figure, and the phase trajectory go to the minus infinity. In theorem 5 and 6, it is proven that the system of differential equation for n equal to is degenerate in the neighborhood of a singular point under condition 1 and is a saddle under condition 2, is a node under condition 3, and is a focus under condition 4 that you can see on this slide. Moreover, the node of the focus are stable of condition 5 holds and unstable if condition 6 holds. In theorem 7, it is proven that the points of conditionally stationary plane one of differential model for n equal to, which arise under the additional condition, are degenerated as the determinant of the system Jacobian matrix at this point is equal to 0. The analytical condition of this next bifurcation, in which an attractor appears in the phase space, includes the coefficients of inter-subpopulation competition, C. In this case, the critical value of parameters is determined by the equality 3, are the parameter when chosen at false the 4. In theorem 8, it is proven that the generate stationary line of a dynamical model for n equal to consists of points of attraction array attractors of the general form 1, this one, and points of repelling array repeller of the general form 2. The composite singular point that combines the attractor of the repeller has coordinates 3 and root of characteristic equation of Jacobian matrix equal to 0 with multiplicity 2. The next bifurcation of the type occur when the parameter pass through the critical value defined by equality 4 and other parameters have been chosen 5. Such bifurcation leads to existence of an infinity number of equilibrium points. The transcriptically of such bifurcation consists of the loss of stability of the non-zero equilibrium point belonging to axis x and in the formation of stable node in the non-zero singular point of the system, which is located on x, horizontal x. From objective point of view, the state is caused by the balance between the level of reproduction of two subpopulations. Taking these into account, a certain retro arises in which there is no dynamics in the system. Based on proven theorems, bifurcation diagrams of the system have been constructed in various parameter spaces. The designation used in previous figure are given in our table that you can see on this slide. Based on the general appearance of coefficients of characteristic equation of the system, we can see that its three special points, uh, the sign depends on the value for parameter. The first is the second is lambda plus lambda 2 minus 1, and C1 divided by the second C. In turn, the sign of these points will determine whether the point will be stable. At the same time, we are interested in the states of the system which positive and negative values of parameters. Uh, First one, the second A, and the lambda plus lambda minus 1. And also when the value of parameter C divided by C2 is less than 0, belongs to the interval from 0 to 1 and greater than 1. The number of phase portraits of the system is equal to 3 times 3 times 3 equal 27. As a result of analytical studies, it was established only 18 types of face portraits are completable and 9 are incompletable, respectively. Based on the symmetry of singular points, was established that 11 types of non-equivalent phase space are possible for system that you can see on this table. Bifurcations of the dimensional system are bigger than one. Usually, the generate states of the system are determined by the critical values of these parameters. It is known that such states can occur when detected G equals 0 and another one. As it was shown in the previous subsections, in case of system that are considered in our paper, the analytical form of invariant determiner of G and is representative as a product of several linear terms. It is obvious then, along with simple bifurcation, complex bifurcations may exist, in which critical values are taken by several invariants of the system and one such case of distinguishment by more complex topologies of these phase states such as focus saddle, node center, and stable node, unstable node, and etc. In theorem number 9, it is proven that the system can undergo the following complex bifurcation of codimensionally bigger than 1. The first one, under the condition that one system undergoes a complex bifurcation of the second type, characterized by bifurcation of codimensionally 1 at its two singular points. The next space show for us under the condition that system undergoes of complex bifurcation of the third type, which is characterized by bifurcation is codimensional 1 at its three singular points. And the next, the last picture, under condition that 3, the system undergoes bifurcation of the third type of codimensional 2, which is characterized by bifurcation of codimensionally 2 of the system at its three singular points. A similar bifurcation of codimensionally 2 occur when the condition 1 are qualified simultaneously. From practical points of view, which such bifurcations are no significant change in dynamics, but qualitative change definitely excite. It should be noted that the separatrix of the origin are placed in a certain angle to the axis, but don't coincide with them. During such critical bifurcations, the topological structure of the face portrait around the origin undergoes the transformation from a node to a saddle. Investigation of nonlinear properties of bifurcation hypersurface on two and three-dimensional parametric spaces of two-dimensional model. The Jacobian matrix of the system when n equal 2 at the singular point of the origin coincides with the Jacobian matrix of the system 1, so we'll classify bifurcation hypersurface only for non-zero singular point. According to the coefficients of characteristic equation presented in this table, a bifurcation of the no saddle type point according to the coefficient of characteristic equation present in this table, bifurcation of non-saddle type as a point occur under the condition 2 to 4. The bifurcation hyperplane 2 excites only on two-dimensional bifurcation diagram, and one of them is it coincides with the axis that you can see respectively. In most cases, bifurcation hyperplanes are nonlinear, and the results of study of the bifurcation hyperplane represented by question number 4 are shown in the table on the B slide and the next slides, 18 and 19. On other parametric fields, the corresponding bifurcation curve is presented in the form of a graph, which is the second order curve. The analytical condition for these terms of the node focus bifurcation transition at the point is as follows. You can see the question number 1. The classification of the corresponding bifurcation curves is presented in the table on this slide and the next slide. 22. Bifurcation of the type stable focus, unstable focus at a point occur under following condition. When reducing equation 1 to the canonical form of the second order curve, the invariance listed on the table. On other parametric spaces of the system number 2, the corresponding bifurcation curve is represented as a graph that is not a second-order curve. Analytical conditions for the occurrence of bifurcation at points are symmetric, and the list of topological structure is the same, so we limit the study of bifurcation hyperplanes to these points. Three-dimensional bifurcation diagrams. The analytical condition for the occurrence of bifurcation in the system at the point is presented in the form from 1 to 3. The bifurcation hyperplane 1 is present only the planes, the first is, the second and the lambda, and the other points. The bifurcation hyperplane 2 excites of parametric spaces on general form. Moreover, there it will pass through the points 1, 0, 0, and the next point 0, 1, 0, and will be parallel to the third axis. Also, the bifurcation hyperplane 3 will be present on all bifurcation diagrams, one of the variables of which the first lambda and the second lambda. On these parametric spaces, this bifurcation hyperplane will be represented by planes perpendicular to the axis, the first lambda and the second lambda, respectively. From the bifurcation condition 1, which contributes to the emergence of the non-focus type bifurcation and non-zero singular point of the system, it can be seen that in most cases and degree of bifurcation hypersurfaces reach 3 and sometimes exceeds the value. This only exception to this rule as bifurcation hyperplane represented by the bifurcation diagram. This table represents for us the result of study of bifurcation hyperplanes on the possible bifurcation three-dimensional measurement diagrams as well as invariants. On other parameter spaces, the bifurcation surface is represented as a graph, which is not second-order surface. The bifurcation arising under condition 1 is characterized by several features. First, since the parameter, the first lambda, is not included in 1, on three-dimensional bifurcation diagrams in which one axis is represented by the constant first lambda, the bifurcation hyperplane will have the form of a cylinder perpendicular to the axis lambda 1. That is why research of corresponding diagrams should be simplified to two-dimensional measurement diagrams. The result of study are presented in our table that you can see on this slide. On other parametric spaces, the corresponding bifurcation surface is represented as a hyperplane which is not second-order surface. As a conclusion, from the present result, it is clear that the model sufficiently adequately describes intradynamic processes that are taking place against of a background of several subpopulations that are not isolated, but at the same time differ among themselves in terms of a habitat and feeding method. The adequacy of proposed model is confirmed by a large number of face portraits and diagrams reflected the condition of quantitative changes in behavior of both the system in general and individual subpopulations in particular. The results show that the key factors in the case interaction of subpopulation with separate niches of the ratio of the coefficient of inter-subpopulation competition. This ratio plays one of the main roles in determining the dominant subpopulation in the system. It should be noted that the system-wide dynamics of subpopulation processes also significantly depends on the reproductive potential of all subpopulation and intra-system dynamics with the reflected in transition coefficient proposed in our paper. Thus, the mass fraction of individuals which according to their phenotypic properties belong to the parent is proposed and work to be called transition coefficient, which in turn belong to the gap and must meet the condition of the closeness and system. It has been established that such subpopulation in real life can exchange offspring, which in turn can significantly affect both the quantitative aspect of dynamics. For example, for a two-dimensional system, the sum of the mean elements for matrix transition coefficients is essential. In the case where the sum is close to the size of subpopulation in the system, the subpopulations have little dependence on each other. In opposite case, the dynamics being much more complex that move to qualitatively different levels. The bifurcation properties of subpopulation dynamic model with the basic Lotka type function were studied. Apply the substantiation of possible bifurcation of the system makes it possible to access the factor that will qualitatively effect of dynamic of the system and to develop a number of recommendations to prevent the occurrence and collapses in the system. Compared with prior studies, the condition for the occurrence of bifurcation equilibrium points of the node saddle, node focus, astable focus, unstable focus types have been determined, and complete classification of bifurcation curves and hyperplanes has been provided with respect to their non-linearity. Thank you very much for your attention.